So question 10, as always, proved to be quite a tricky question for most students on this exam. So let's have a look at it. So question 10 says, let f go from 0 to infinity, mapping to the reals, such that f of x equals 2e to the negative x on 5. A right-angled triangle, so the right-angled triangle here that I'm drawing in green, has the vertex O at the origin, Q on the x-axis, and P on the graph of f as shown. And the coordinates of P can be written as x comma f of x. And what we're asked to do is find the area, so I'll shade that in, of the triangle. And we want to find that in terms of x. So the area of any triangle, area of a triangle, is equal to a half times the base times the height. So in this one, we know that our area equals a half times the base, where our base is just a length denoted by x, by the height, which is f of x. So the distance there is f of x. So, of course, we know that that gives half x times our f of x, which we know up here is 2e to the negative x divided by 5. So the 2, I'll put it in red, the 2 there and the 2 there cancel, just to leave that the area is equal to xe to the negative x on 5. And that's the answer to part A of this question. So 55% of kids got that right. It probably wasn't that hard. You should probably expect to get that sort of question in future. It's really applying quite basic maths from years 7 and 8, just in a new unfamiliar context. So we've previously found the area here, and it asks us find the maximum area of the triangle OQP and the value of x for which the maximum occurs. So what we need to remember is that we expect a maximum to occur when dA dx equals 0. So the first thing we need to find is dA dx. So we've got area equals x times e to the power of negative x on 5, which is going to be a product rule. So we're going to need to apply a product rule to this. And we know that our product rule, I might just get rid of that, says that dy dx equals u dot dv dx plus v dot du dx. And for this, we're going to use the substitution that u equals, might move that over here, u equals x and v equals e to the negative x on 5. So du dx is just equal to 1, and dv dx is just equal to, so the derivative is going to be negative a fifth, so we bring the coefficient out, e to the power of negative x on 5. Hopefully I haven't got anything wrong there. So now using our equation, we have what I'll call is dA dx equals, so u is x times dv dx, which is negative a fifth e to the negative x on 5, plus v, which is e to the negative x on 5, times du dx, which is just 1. So if we simplify that, we just get dA dx equals, so I'm going to pull the e to the negative x on 5 out the front, and we're going to be left with negative x on 5 plus 1 inside the bracket. So now what we've said is we're expecting that the maximum occurs when this equals 0, so we can write therefore e to the power of negative x on 5 outside of negative x on 5 plus 1 equals 0. And now we know that using the null factor law, we could have e to the negative x on 5 equals 0, or minus x on 5 plus 1 equals 0. So I'll just separate those two bits of working. So we know that this can never equal 0. Alright, because we can't have log of 0 if we take our equivalent log statement. We get log e of 0 equals negative x on 5, and that's undefined. So we get an undefined answer for that. So the answer must lie in the second one, which gives us negative x on 5 equals negative 1, therefore x equals 5. Hopefully that looks alright to me. So now that we've got x equals 5, what we need to do is find the maximum area. So we need to find the maximum area of the triangle. So we know that area was given by this equation up here, and we just need to sub 5 into that. So the maximum area occurs at 5 times e to the negative 5 on 5, which is just the same as maximum area equals 5e to the power of negative 1, which is just 5 on e units squared. So 5 on e units squared is the answer to the question. So part C says let S be a point on the graph of f on the y-axis, and let t be a point on the graph of f with the y-coordinate a half. Find the area of the region bound by the graph of f and the line segment st. So this was particularly difficult with only 7% of kids getting it right, and I can hardly blame the other 93% for not getting this one, because it is a really tricky question. But at the end of the day, it is actually quite doable in terms of the Maths Methods course. It just takes a lot of persistence. So what we're essentially saying is we want to find the area that's shaded in green here. That's our end goal for this question. So the first thing that I want to do is find the coordinates of the point S and the coordinates of the point T. So for S, we have S has an x coordinate of 0 and a y coordinate that we'll find in a minute. So to find the y coordinate, we're just going to go y equals 2e to the power of negative 0 on 5. And we know anything to the power of 0 is just 1, so that equals 2. So we've got S is 0, 2 there. I'll just put that in there as well for us. And now we also want to find the coordinate of t. So t is going to be a little bit trickier to find because we know that t is something comma a half. So we need to solve the f of x equation for when y equals a half. So we're going to set up a half equals 2e to the negative x on 5. And that'll give us the coordinate of t. So if we divide both sides by 2, we get a quarter equals e to the negative x on 5, and then we can take an equivalent log statement of that. So we get log e of a quarter equals negative x on 5. So therefore we can say x equals, so multiply both sides by negative 5 log e of a quarter. And then if we really want to, we can use our plug law to take the negative up to the top there, and we can rewrite this as, therefore, x equals 5 log e of a quarter to the power of negative 1, which is just 5 log e of 4. So, just to consolidate what we found, that t is at 5 log e of 4, comma, a half. So, now that we've got those 2 points, we can start to unpack more of this question. So I'll just get us a little bit of new space and write in what we found. So we found that that was at x is 0, y is 2, and t was at 5 log e of 4, comma, a half. And we remembered that our equation f was given by the following. So now I'd suggest that we define an equation for the line segment ST. So I'll put that in blue. So what I'm going to do is I'm going to find an equation y equals mx plus c, which describes to describe ST. So the first thing I'm going to do is I'm going to work out what the gradient is. So my gradient m equals y2 take y1 over x2 take x1. So y2 doesn't really matter which order we go in as long as we keep it consistent. So I'm going to say that's 2 take a half over 0 take 5 log e of 4. So that's going to give me 2 take a half, leaves me with 3 on 2 over 5 log e of 4, which if I clean it up a little bit further, sorry, that's a minus 5 log e of 4, just rechecking over my work. I'm going to get minus 3 on 10 log e of 4 as my gradient. So that's the gradient of the line up here. The next thing I need to do is work out what the plus c value is. So I can rewrite my equation to be y equals minus 3 over 10 log e of 4 times x plus c. And now what I'm going to do is I'm going to sub in a point, and I'm going to select the easiest one, 0, 2. And that will let me solve for the plus c value. So when x is 0, y should be 2. So therefore 2 equals minus 3 over 10 log e of 4 times 0 equal plus c. Therefore c equals 2 implies that ST can be described as minus 3x over 10 log e of 4 plus 2. So that's the blue equation up the top that describes my line segment. And this is going to come in very useful when we're doing our area above and below the curve in just a second. So I'll just grab a new bit of space for us to play around with and again write out what we found. So remember, we've called that point 0, 2. That point was 5 log e of 4, comma, a half. And that blue line segment is described by the equation y equals minus 3x divided by 10 log e of 4 plus 2. So now again, we're hunting down this area in green, or shaded in. And we know that that area is going to equal the integration between our x point 0 here and 5 log e of 4 of our upper curve, which is the blue, minus our lower curve, which I'll put in red, which is that function there. So that's how we're going to find the area of the green. So just to make that clear, we're going to say that our area equals the integral between 0 and 5 log e of 4 between my upper curve, which I said was minus 3 outside of 10 log e of 4 x plus 2, minus our lower curve, which is 2e to the power of negative 5 on 4, all with respect to x. So just to make that really clear, that's the integral that we're going to try and process now. So in order to do that, we need to find the integration of the blue part and the red part. So we know that the area, the green area that we're looking for, is equal to, so if we anti-differentiate this, we get minus 3x squared divided by 10 log e of 4, and then we halve that because of the new power we've introduced. So the blue is going to turn into minus 3x squared divided by 20 log e of 4 plus 2x divided by 1. And then we're going to subtract away the integration of the red, which is going to be 2e to negative x on 5, and we're going to divide that by negative 1 on 5 to get the integration that we want. And then we're going to evaluate that between the 0 and 5 log e of 4, the two x coordinates that bind the shaded green region for us. So unfortunately, this is going to take a fair bit of pumping through of just mathematics. So we'll get stuck into that and we'll just go through nice and consistently until we've got our answer. So the first thing we're going to do, I'll just grab another bit of paper and rewrite what we've got, just so we can start fresh. So grab a new piece, and we said that our area is equal to, so minus 3x squared divided by 20 log e of 4 plus 2x, and that was our blue. And then we were going to subtract away 2 divided by negative a fifth, which actually turns into plus 10. So you can go back and check on the previous screen that we had. It's going to turn into plus 10 e to the negative x on 5 between, we said 5 log e of 4 and 0. So again, our area is just going to be equal to substituting in the blue to here, and then substituting in the green, might do this in orange, doesn't really matter, substituting the orange into here. So that's just through the fundamental theorem of integral calculus. So subbing in 5 log e of 4, we get for the blue part minus 3 5 log e of 4 squared over 20 log E of 4 plus 2x, which becomes plus 2 times 5 log E of 4 plus 10e to the negative 5 log E of 4 divided by 5, and that's the blue. And then we subtract away from that the orange, which is going to be 3 times 0 squared divided by 20 log E of 4 plus 2 lots of 0 plus 10e to the negative 0 on 5. So you'll probably notice that the orange is going to be a lot easier for us to simplify down. So this is worth 0, this is worth 0, and the e to the power of 0 is worth 1. So we've got 10 times 1 in the whole orange. The blue, however, we're going to have to keep plugging away at to make it make sense of something. So let's grab another line of working. So the area in the blue is equal to, let's see, minus 3 times, we could distribute that, 5 squared log E of 4 squared. So overall, we're going to just simplify that to minus 75 log E of 4 times log E of 4. So again, that that minus 75 is minus 3 times 25, and then I've just split log E of 4 squared into 2 lots of the log E of 4's multiplied together. Then divide off by 20 log E of 4, and we can see that one of these will cancel with the bottom line. Then the next part of the blue just gives me plus 10 log E of 4. And then the third term, which I'll just underline in yellow that we're up to, we can simplify that one down to 10, let me see, so the 5's will cancel for that, and we'll just be with 10e to the negative log E of 4, which I can write as plus 10 plus 10e to the log E of the 1/4. So I'm just going to take the negative up into the 4 and use that reciprocal law to turn into a quarter. And then we know that E log E sort of undoes itself. So all we're left with here is 10 times a quarter. So that 10 times a quarter, if I just quickly do it in a separate color, maybe bring black in, that's just 10 times 1/4 now. So now that we've got our 10 times a quarter, we just reintroduce the orange, which is minus 10. And we keep cleaning up a little bit. So our area equals, so we've still got minus 75 log E of 4 on 20 plus 10 log E of 4 plus 10 times a quarter, so 10 quarters minus 10. So now I'll just grab a little bit more space, and we can see our previous result was that we had minus 75 log E of 4 on 20 plus 10 log E of 4 plus 10 on 4 plus 10, which I'm going to write as plus 40 on 4. Sorry, that was a minus from our previous one, just check. So that's minus 10, which is minus 40 on 4. So now, keeping on cleaning up, we can turn this into minus 15 log E of 4 on 4 plus 40 log E of 4 on 4 minus 36 on, plus 10 minus 40 is minus 30 on 4. And now clean up a little bit further, and we get that this is 25 log E of 4 on 4 minus 30 on 4. And if you're really pedantic, you could turn it into 25 log E of 2 squared on 4 minus 30 on 4. And if we bring the 2 out, our final answer could be 25 log E of 2 on 2 minus, clean this up, to be 15 on 2. And that's the final answer for this very tricky question that only 7% got. Only 7% got this answer. So don't feel too bad if you couldn't get all the way to the end, but hopefully you could pick up a few of the marks for this question.